What if I told you there's a new kind of computer out there, one so powerful it could tackle problems that our best supercomputers today literally can't solve? Well, that's not science fiction anymore. We're about to dive into Google's Willow chip, and trust me, it's a breakthrough that represents one giant leap toward that incredible reality.
Okay, just look at this number. That's 10 septillion. It is an impossibly big number to get your head around. I mean, it's more than the number of stars we can see in the entire universe. And according to Google, that's how many years our fastest supercomputer would need to grind away at one very, very specific problem. 10 septillion years.
So how in the world is that even possible? Well, the answer is a brand new quantum processor from the folks at Google AI. It's called Willow, and it's not just a little faster. It tackles one of the biggest, most fundamental roadblocks in the entire history of computing.
All right, so to really appreciate what Willow just pulled off, we first have to understand the central puzzle that has been holding back quantum computing for decades. It's this paradox that kind of seemed unsolvable.
Here's the core of it. With our normal computers, it's simple. More transistors, more power. Easy. But in the weird world of quantum computing, the building blocks, these things called qubits, are just unbelievably fragile. So for years, every time scientists tried to add more qubits to make the computer more powerful, it just introduced more noise and more errors, making the whole system less reliable. The holy grail, the dream, has always been to flip that script, to finally get to a point where more qubits actually means more reliability.
So how do you do that? Well, the big idea is a theory called quantum error correction. And the concept itself is just brilliant. What if you could take a whole bunch of those shaky, unstable physical qubits and kind of force them to work together as a team? The goal is to make them act as one single, super stable, self-correcting logical qubit. It's kind of like building one perfect, flawless brick out of a whole pile of slightly cracked ones.
And that, right there, brings us to Willow. This is the moment where that amazing theory slams into reality. Google's new chip takes a monumental step forward, making quantum error correction a physical, tangible thing. Let's look at how they did it.
So this is it, Willow. It's a new superconducting quantum processor, and its secret sauce is something called the surface code approach. You can basically think of it as a super-specific, grid-like blueprint for arranging all those little physical qubits. It lets them constantly check in on each other, find errors, and correct them as a team, all to form that one, stable, logical qubit.
Now, to prove this actually worked, the Google team didn't just build one logical qubit. That wouldn't be enough. They built several, each one bigger than the last. They started with a 3x3 grid of physical qubits, then scaled up to a 5x5, and then all the way up to a 7x7. The big question, the one everyone was holding their breath for, was, would bigger actually be better? Or would it just fall apart with more errors, like it always had before? And the result was a resounding, massive success. Just look at this chart. As they scaled up from the small lattice to the medium one, and then to the large one, the error rate dropped by roughly half at each step. This is it. This is that exponential improvement everyone in the field has been chasing. For the very first time, they proved it. Adding more physical qubits actually led to a more reliable logical qubit. They cracked the scaling problem. This is what experts in the field call entering the below-threshold regime, and it's a huge deal. The industry analyst Forrester even called it one of the holy grails of quantum computing. It's a crystal-clear signal that the fundamental science is solid and the engineering is finally starting to catch up.
Okay, so this is obviously a massive achievement. But to really understand what it means for us in the real world, we need to add some really important context. So let's break down what this breakthrough means today, and maybe more importantly, what it doesn't mean, at least not yet.
All right, let's unpack Google's core claims. First up, error suppression. They prove that as you make the logical qubit bigger, it actually gets better and more reliable. This is absolutely vital because it shows there's a real credible path to building large-scale, stable quantum computers. Second, that mind-bending benchmark speed. That demonstrates something called quantum supremacy, which is just proving that a quantum device can solve a problem that no classical computer could even dream of touching. And finally, by calling this a major step toward a useful computer, they're basically sending a message. This isn't just a science experiment anymore. We're on a real engineering roadmap now.
Now for the reality check, because, we're not quite there yet. The trend of falling error rates is fantastic, but the error rates themselves are still way too high for a truly massive, useful computer. And that benchmark problem, it was a very specific problem designed to show off the hardware. It wasn't a practical, real-world application like designing new drugs. That's the key difference between supremacy and advantage. And, critically, for anyone worried about cybersecurity, Google is being very clear. This machine cannot break modern encryption like RSA, not even close. Getting to millions of qubits is going to bring a whole new set of engineering headaches.
So with all that context in mind, let's zoom out. What are the long-term implications of what Willow has accomplished? Where does this whole journey go from here? For technology and for all of us.
See, this isn't just about one chip in a lab. Its success sends ripples absolutely everywhere. By proving that this scaling approach works, it's basically a giant green light for major investment from both governments and private industry. That, in turn, solidifies the path toward finding real-world uses, everything from designing new medicines to creating revolutionary new materials. The message to the entire tech world is loud and clear. The quantum era is coming, and it's time to get ready.
So, what should you be looking for on the horizon? Well, first, watch for those error rates to keep dropping, especially for actual operations, not just for storing information. Also, keep an eye out for the development of actually useful algorithms that go beyond these carefully chosen benchmarks. And of course, the big race is on to scale from hundreds to thousands, and then eventually millions of qubits. And on the other side of the coin, watch for progress in quantum-resilient cryptography, the new security we're going to need to protect us in this future.
So no, Willow isn't the final destination, but it is an absolutely critical milestone. It's the kind of progress that makes the end of the journey feel so much closer. It basically transforms a huge part of the quantum dream from, well, we think this should work, to, we have now proven it can work. And that very long road to a truly useful quantum computer, it suddenly feels a whole lot shorter.
So there you have it. A fundamental barrier has been broken. The pace of development is only going to get faster from here. And the question is no longer if we'll have these incredibly powerful quantum computers, but when. The bigger question now is, are our industries, our security systems, and our society as a whole ready for what comes next? Thanks for joining me for this explainer.